Now, today we have discussed about 6.5 work done by a variable force. Many time what happen? Suppose one body is there. Now this is the body. You have to apply the force on that body. In that case, first you have to apply some force. Then next you have to increase the force. Then what happen? The displacement is also increases. Means many times you can't apply a constant force. Means you can apply first initially 2 Newton force, then you have to increase the applying force and 3 newtons, 4 newtons, 5 newtons, and again you have to increase, or sometimes you have to decrease to apply a force. Many times you can't apply on a body for a constant force. For that purpose we have to find out the work done by a variable force. Means we can't apply a constant force for a long time. In that case we have to find out the work done by a variable force. Now consider that if the displacement delta x, we can take a force if the displacement is delta x. For that displacement the force is doing the displacement. For that displacement, the applied force, the force is Fx. Means we have to apply the force Fx, then the body will be displaced. That displacement is delta x. Okay, whatever delta x will be displacement. Okay, to do the delta x displacement, for that purpose whatever the force applied, we have to say that force is Fx. Then work done by this force. Then work done by this force is work done by this force. This force Fx is, that is work done is equal to Fx into delta x. You know that work done is nothing but force into displacement. In that case, to do a displacement means the body displaced is delta x by applying a force Fx. Then work done is W is equal to Fx into delta x. Now this is the equation 1. Okay. Then for a variable force, okay, okay, in that case, now see here, this is the graph, this is the displacement x, and this is the Fx along y-axis, displacement along a x-axis, and force along a y-axis. Now we have to consider that the force is a variable force. Now see here, in that case, first we are whatever applying force, the first initially the force will be increases, then force will be decreases. Means the force will be a vary. Means the value of a force, value of applied force is varying. For that purpose, this is known as a variable force. Firstly, the force will be increases, then decreases, or similarly, firstly force decreases, then increases, whatever it may be. Means sometimes it is increase, decrease continuously. Means in that case, the force will be changed. Means the applied force is changed. In that case, this is the graph between displacement and force. In that case, here the force is along y-axis. Then this is the applying force is vary. Force is vary. In that case, see here, if you consider a small displacement, okay, if you consider a small displacement delta x, okay, if you consider a small displacement, in that case this is the force. Okay, when you applied a small displacement, then what happened? The work done, the applied force is remains a constant. Okay, for small displacement, applied force assumed to be a constant, means looking like as a constant. Assume to be a constant. Assume to be a constant. Okay, means if you see a small displacement, okay, in that case the applied force is looking like as a constant. Okay, in that case the work done, the total work done, in that case the total work done, in that case the work done for a small work done, for a small displacement, whatever work done is there, that work done is a small work done delta W. In that case the total work done. Okay, now this is the work done for this small displacement. Okay, this is a delta x. For delta x, whatever work done is, that is fx into delta x. Then we have to find out a total work done. In that case, suppose this is a delta x, then again a one small delta x, 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 again a one small delta x. In that case there are many delta x. Now initial point, this is a initially xi and this is the final xf. Okay, in that case the total work done, now in that case the total work done means the work done by a first small delta x, work done by a second small delta x, work done by a third small delta x. In that case the total work done W is equal to summation of this work done, means work done for this small delta x plus work done for this small delta x, work done for this small delta x, work done for this, and so on. Therefore this is the summation, means addition of xi to xf fx into delta x. Okay, see here, in that case for a small delta x the work done is small delta W, which is equal to fx into delta x. Okay, in that case the total work done, okay, for a small displacement, whatever the force is there, the force is also looking like as a constant. Okay, in that case the total work done is a for a first work done plus second work done, third work done, fourth work done, and so on. Therefore total work done is equal to summation over xi to xf fx into delta x. Now this is the equation 2. Now we have to decrease the displacement, means we have to decrease the delta x. Whatever delta x is there, we have to divide that delta x into a very small pieces. In that case that delta x is approaches to a 0. Okay, now we have to increase, or now we have to decrease delta x values. Then if you have decreased the delta x value, then what happens? The number of partitions is also increases, means the number of partitions is increases. If you have decreased the delta x value, means if your delta x value is small, if you have decreased the delta x values, the partitions increases. Okay, if you have increased the delta x value, the partition increases, then it look like figure B. Now this is the figure A. Now it look like a figure B. Okay, then if you increase the partitions, okay, if you increase, it means delta x is decreased, means small delta x the partition ఇది చేసిన తర్వాత this is the total work done. Okay, now this is looking like as a figure B, means this is the xi and this is the xf. We have to increase the partition, then means if you decrease the delta x value, then what happen? All that small partitions are there, and this is a totally becomes a plane. Then the limiting value, then the work done is, for limiting values approaches to definite value and is given by work done is equal to limit delta x approaches to 0 fx into delta x. Now this is work done is equal to limit delta x fx into delta x, limit delta x tends to 0, and this is the summation over xi to xf, limit delta x tends to 0, summation over xi to xf, fx into delta x. Now this is converted into integration over xi to xf, fx into dx. Now this is the work done for a variable force. Now this is the equation 3. Equation 3 is the work done for variable force, work done by variable force, work done by a variable force. Please only understand this work done is equal to work done w is equal to integration over a limit xi to xf, fx into delta x. This is the work done by a variable force. Now next point, the work energy theorem for a variable force. In previous point we have discussed that the work for a variable force, the work done by a variable force w is equal to integration f into delta x or f into dx. Now today we have discussed about the work energy theorem for a variable force. Then now we have to start. We know that the kinetic energy is given by kinetic energy of a particle is given by, what is the kinetic energy? K is equal to half m into v square. Now this is the equation number 1. We have already know the kinetic energy K is equal to half m v square. Now differentiating equation 1 with respect to t, differentiating equation 1 with respect to t. Okay, this is read as with respect to t, means differentiating equation 1 with respect to time, that is d by dt of k is equal to d by dt of, that is right hand side is half m v square. Means we have to differentiate equation 1 with respect to t in both sides, that is dk by dt is equal to d by dt of half into m v square. Left hand side as it is dk by dt is equal to, now differentiation of half m v square, half m is common, only a differentiation of v square, that is d by dt of v square. Half is constant, mass of the particle is also constant, half m is constant, d by dt of v square. This is equal to dk by dt is equal to half m. Okay, what is the differentiation of v square? Differentiation of v square with respect to dt. Okay, velocity is depend upon time, therefore first we have to take a differentiation of v square. Differentiation of v square is 2 into v. Differentiation of v square is, do you know that differentiation formula? By using that formula, differentiation of v square is 2v, okay, again into differentiation of this v. Differentiation of v square is 2v. Now this is the differentiation with respect to t, therefore again we have to differentiate this v with respect to t, that is dv by dt. Okay, d by dt of v square is differentiation of v square is 2v, then again this differentiation of v with respect to t, that is dv by dt. Now this is equal to half into m. Okay, then dv by dt, do you know that dv by dt is nothing but a acceleration. dv by dt is nothing but a acceleration. Okay, therefore into this is a 2v into dv by dt is nothing but a acceleration. In that case 2 and this 2 is cancelled, then this is nothing but m this a into v. I can write this is equal to m a into v. Therefore dk by dt is equal to m a v. See here differentiation again I can explain once again. dk by dt is equal to half m. Okay, only this half m is constant, therefore we have to taking outside of differentiation. Then d by dt of v square. Okay, then differentiation of v square is 2v. differentiation of v square is 2v. Then again we have to differentiate this v with respect to t, that is dv by dt. Then you know that dv by dt is acceleration. Remaining parts is as it is, half m 2v as it is. dv by dt is nothing but a acceleration. These two cancel. Then m into a into v. Then you know that using Newton's second law, mass into acceleration is nothing but a force. Therefore dk by dt is equal to f into this v. Okay, f into v. Here which law we have to use? Using Newton's second law. Using Newton's second law. Now this is the equation 2. See here this mass into acceleration is nothing but force. Using a Newton's second law, mass into acceleration is nothing but a force. Therefore dk by dt is equal to f into v. Okay, then again you know that, no, this is not, again we know that v is nothing but dx by dt. Okay, therefore dk by dt is equal to, then you know that v velocity is nothing but dx by dt. Therefore f into dx by dt. Since we know that v is equal to dx by dt, velocity is nothing but dx by dt. Therefore in place of v I can write dx by dt. Okay, now this dt both are in numerator, therefore we have to cancel. Therefore this is equal to dk is equal to f into dx. Now this is the equation number 2. Now we have to integrate this equation within the limit. Okay, integrating equation 2 within the limit. Now we have to integrate this equation within the limit. Then integration of dk is equal to integration of f into dx. Now what is the kinetic energy? Integration of dk, k is the kinetic energy. What is the limit of kinetic energy? This is the initial kinetic energy to final kinetic energy. These are the limit. Now this is integration from xi to xf. Okay, this is the integration with respect to dx. Integration of f into dx. X limit is initial displacement and final displacement. Okay, therefore then you know that. Okay, this is the equation 3. Then we have already know that integration of f into dx. Integration of f into dx is nothing but a work done. Okay, integration of f into dx is nothing but a work done, and in that case whatever differentiation, this is the differentiation and integration, both are cancelled. Differentiation and integration are cancelled. Therefore only a kinetic energy. Kinetic energy having a lower limit is ki and upper limit is kf is equal to right hand side integration f into dx having a limit xi to xf. We have already discussed this is a for a work done for a variable force. The right hand side is a work done for a variable force. Therefore this is equal to work done. Then the kinetic energy having a limit ki, k initial to k final is equal to work done. Then put the upper limit minus lower limit, that is kf minus ki is equal to work done. This is the equation number 4. Okay, kf means the final kinetic energy, Ki means a initial kinetic energy. Therefore this is nothing but change in kinetic energy is equal to work done. Now this is the equation 4. This is the change in kinetic energy is equal to the work done. This is known as a work energy theorem for a variable force. The equation 4 gives that the change in kinetic energy, delta K is nothing but final kinetic energy minus initial kinetic energy. The change in kinetic energy is equal to the work done, and therefore this is known as a work done for a variable force. This is the work energy theorem for a variable force. Now this is the equation 3 is the work energy theorem for a variable force. Okay, now see here, this is the integration of delta k, k having a limit, kinetic energy having a limit, initial kinetic energy and final kinetic energy. In that case, the integration of delta k having a limit k initial to k final is equal to integration of f into dx. What is the dx? What is the x? X limit is initial position to final position, xi to xf. Therefore right hand side integration of f into dx having a limit xi to xf is nothing but a work done. Therefore work done is equal to this integration and differentiation is cancel, only kinetic energy is there. Kinetic energy having a lower limit is ki, upper limit is kf. In place of k you have to put a kf minus, okay, that is upper limit minus lower limit is equal to work done. That is a final kinetic energy minus initial kinetic energy is equal to work done. Final kinetic energy minus initial kinetic energy is nothing but change in kinetic energy. Change in kinetic energy is equal to work done. This equation 4 is known as a work energy theorem for a variable force.